Hello again. This is video 2 of Unit 1, which will deal with the classification of organometallic compounds. Organometallic compounds may conveniently be classified by the type of metal-carbon bonding that they contain, ionic or covalent. Carbon is a fairly electronegative element. According to the electronegativity of carbon, 2.5 on the Pauling scale, it is expected to form ionic bonds only with more electropositive elements and covalent ones with the rest. The periodic table may be divided into very approximate regions into which the various types of organometallic compounds predominantly fall. Such a classification, this one you've got here, is not rigid, and the regions overlap. It should be noted that in the transition metal organometallics, in the D series, the bonds involved are not only sigma, but also pi and delta, which is not commonly found amongst compounds of the main group elements. In addition, the transition metal organometallic chemistry is practically dominated by the ligand characteristics rather than by the position of the metal in the periodic table, as we will see. Therefore, transition metal organometallic compounds will be studied separately from those of the main group elements. Organometallic compounds containing metal ions generally are formed only by the most electropositive elements, that is, by the heavier alkali metals. They crystallize in real ionic networks, such as sodium chloride, cesium iodide, etc., and exhibit low or negligible solubility in non-polar, non-coordinating solvents, also a high reactivity and poor stability. Pay attention, they react with those solvents that possess acid hydrogens, such as alcohols and amines. On the other hand, alkanes, that is, saturated hydrocarbons, are the only appropriate means of reaction, that is, the only solvents you can use with these compounds. This high reactivity is due to the pronounced carbanionic character. They are very sensitive to oxygen and water. With water, they react violently, forming the corresponding metal hydroxide and also hydrocarbon, which may be flammable. The formation of ionic compounds is favored when the hydrocarbon anion may be stabilized by the localization of the negative charge over several carbon atoms in an aromatic or unsaturated system. This applies to sodium cyclopentadienide and also to trityl sodium. In the cyclopentadienide anion, 6 pi electrons form a delocalized aromatic system. With cations of electropositive metals, these stable anions can form salts which have a high degree of ionic character. In sodium ethinyl, the negative charge is stabilized mainly on account of the greater electronegativity of Sp relative to sp3 hybridized carbon atoms. The simplest type of metal-carbon bond consists of an essentially covalent single 2-electron sigma bond. It is formed with carbon by elements with p orbitals of the main groups, as well as, in some cases, transition metals. The polarity of this bond depends on the metal and, to a lesser extent, of the organic ligand. Stability against water depends on the polarity of the bond. You will find the names of these different groups that form this kind of bond in your slides. Do not forget to have a look at them because we are going to work with them along the course. Within any main group of the periodic table, the metal-carbon bond energy falls with increase in atomic number. Binary alkyls and aryls are known for all the main group elements. However, analogous derivatives of d-block transition metals generally cannot be isolated or decomposed readily. This lability is due to kinetic factors and not to any inherent weakness of the metal-carbon bonds. Besides, also in contrast to the main groups, bond energies increase down any group, so that the strongest bonds are formed by elements of the third transition series. This difference can probably be explained in terms of the extent of overlap between the orbitals of the metal and the 2s or 2p orbitals of carbon. In the main groups, the best overlap with carbon orbitals is achieved by elements in the same row as carbon, and down any group the overlap becomes weaker. On the other hand, in the elements of the first transition series, the 3d orbitals are strongly contracted and do not interact as strongly with carbon orbitals as do the larger 4d or 5d orbitals in atoms of the second and third series. Transition elements form complexes with formal double metal-carbon bonds, carbenes, or triple metal-carbon bonds, carbines. The pi components of these bonds are thought to arise through interaction between the metal d orbitals and carbon 2p orbitals. We will deal with these compounds in Unit 8, where we will study the bonding and other differences between those of Schrock and Fischer. The last group we will see in this video is that of complexes of unsaturated hydrocarbons. Transition metals form an enormous range of complexes with unsaturated hydrocarbons. This is one of the main features which distinguishes their organometallic chemistry from that of the main groups. In these compounds, the metal-carbon bonding is essentially covalent in character. It arises by interaction between the pi electron system of the organic ligand and the metal n, p, and d valence orbitals. The cyclopentadienyls comprise the largest group. Are you already able to give a name to all these ligands? We will work on them in class. Thank you for your attention.